بسم الله الرحمن الرحیم. الصلاة والسلام على محمد وعلى الطاهرین. السلام علیکم. مستر عباس، مستر زلال، مستر لمعه، مستر سبا، مستر سرا و مستر یاسر علی. مثلا سلام مستر عباس. Okay, we continue about this the part 3. سلام. اهلا وسهلا. SPD review. We was telling what is image restoration and distortion due to sensor noise, out of focus camera, due to motion blur, weather conditions, scratches, holes, cracks, etc. inside the images and others. We said about the methods, deterministic or stochastic or not deterministic. Okay, Mr. Yasser, نعم. Inshallah today, some problem, okay? Previous to this, to today. Inshallah اليوم. Deterministic and non-deterministic or stochastic, and another view, blind, non-blind, semi-blind. Okay, Mr. Yasser. Yes, Ahmed. Or about implementation methods of methods that was direct or iterative, such as machine learning, okay, deep learning, etc. Direct, some methods directly applicable over the images itself. Some historical notes. We said, for example, some data of FIOJ, a picture, is entering a system for disturbance or in Arabic اعوجاج, okay, or for تخریب, and this is, for example, H in that system, and in the non-blind system we have this H, frequency response of this, for example, or response of this system, and maybe or in real life all times adding with a noise level in a IOJ and the resulted image, okay, or the bad image or corrupted image. Why? And we was finding this R system. Again, repeat it. This R system, a reverse system, okay? If we had the H system, we are finding this reverse system to converting the Y to F hat or a تقریب, okay, or near F as the exact FIOJ. F hat IOJ as near as the FIOJ. We are finding this reverse system in the restoration part. Salam, Mr. Zubaydi, Ali Zubaydi. That's right. We said that linear and space invariant or LSI systems, you have, for example, in this system H K1 F1 plus by K2 F2 is H K1 H F1 plus by K2 H F2, and this is for linearity, and this H Fi minus 0 and J minus J0 yields to Y I minus I0 and J minus J0. We said about advantages that is very good, and we are for example supposing, if possible, all of the systems LSI or in another scope LTI, linear time invariant systems, but maybe in some situations we can't or cannot suppose as this, okay, due to, for example, some constraints of the system, non-linearity or non-space invariant, okay, or space variant. That's right. We said if we had a LSI system, linear time space invariant, we can apply the convolution, the very important and useful relation of convolution. For example, for resulting output of a system when we had its response and or impulse response and its input. Okay, that means this is the convolution system or convolution relation. Y I J is sigma over K and sigma over L, F K over L, H, for example, I minus K and J minus L plus N, or sigma sigma H IOL, H IOL, F I minus K and J minus L. The same, not difference. Okay, and this is the notation. F convolved by H, okay, and maybe plus by some noise value. For example, we spoke about motion blur, okay, and we motion blur is some types of this distortion or some types of edge. Okay, edge is the impulse response of that bad system. Okay, or a system with some disturbance. Motion blur. For example, we said about one dimension. One dimension isn't useful for picture, but we say about one dimension for making the two dimension. Okay, one dimension uniform motion blur. H HI is some constant in some for example domain, okay, and zero otherwise. For example, BI between minus L and L, H is 1 over 2L plus by 1. Why? Because this duration is 2L plus by 1. Okay, this duration multiplied by this weight is 1. Okay, this is a normalized system response. That's right. But this is important. Two-dimensional uniform motion blur. H is I and J between these domains. For example, minus 5 plus 5, minus 7 plus 7, minus 3 plus 3. Okay, minus L plus L, 1 over 2L plus by 1 powered by 2 that we said. This example, this example, this example. Okay, this is a weight window, weighted by 1 in this domain, in this square, and weighted by 0 in our spaces. Okay, this is the system response, H, or impulse response of the system, H small. Another one, atmospheric turbulence. Okay, for example, this image, this good image, and this disrupted, for example, image. Okay, this type of degradation. And the formula, for example, we said about this turbulence, H is, these are some, this is the non-blind method. Okay, we have H of the system. Okay, H impulse response of the system is, for example, K exponential of this is a Gaussian formula, exponential of minus I2 plus by J2 over 2 sigma 2 or variance. This is a Gaussian formula. That's right. And we said about some, for example, not for example, disturbance or no overcharge. Okay, for example, is 0 and K large and K small. Okay, large, medium, small. We know that small case is the same as the 0K. Okay, this is the we see a good view of this system or result of this system, atmospheric turbulence. Another one, we said about uniform, for example, out of focus blur. Okay, and we said is as the same as that windows. Rectangle windows, here is a circle windows. Okay, h is again 1 over constant, pr is a constant. Okay, and I2 plus by j2 is this is a formula for a circle. I2 plus by j2 is smaller than a r2 and 0 otherwise. This is the same as that one, but this weight is a circle. Okay, outside of this circle is 0, weight is 0. This one weight is 1. Salam Mr. Ahmed. Salam alam salam. Okay, no, this two slides was from the last session. Okay, we had BSNR or blurred signal to noise ratio. Okay, we said BSNR is for example we are investigating the result of or the effect of noise. Okay, a system with noise or a system with without noise. This is in logarithmic version. For example, 10 log 1 over mn. Okay, sigma I sigma j z by noise minus z or z. This is the meaning of expected value. Okay, and this is the energy of salam Saudi, salam alam salam, salam. This is the energy of a system. Okay, energy of the system, expected value sigma x minus x bar powered by 2. This is the variance of the system or signal. Okay, and this is variance of noise, signal to noise ratio. Okay, but a system with a blurred, that is the output of the system. Okay, z is y minus n. That means the output without the effect of the noise. Okay, output itself, blurred output itself, damaging only by h, not by n. This is the expected value or variance of that system. Okay, or the blurred signal, and this is the variance of energy of the noise, energy of the signal, blurred signal over the energy of the noise. This is BSNR, blurred signal to noise ratio. And another item, ISNR. Okay, for example, the performance of this system. For example, here, improvement in signal to noise ratio. This system, okay, this reverse system, R system, is better or not, is bad. Okay, here you see ISNR is sigma over I and j in 2 axes, F minus Y, okay, energy of, and F minus F hat. What is this? This is with R system, reverse system, and this is without reverse system. If reverse system, existence of reverse system is good or bad, okay, or ISNR is negative or positive. That's right. And from here we start. This was some overview. Linear convolution, but because image is an two-dimensional signal or random variable or phenomena, we start with again with one-dimensional and again go to two-dimensionals. Okay, linear convolution. After it, we go for circular convolution, and these two items in one-dimensional and two-dimensional. But some of these items may be review for you, and maybe you had these items in your undergraduate. That's right. Linear convolution for one-dimensional signals. Okay. In this section, we need the concept of linear convolution in order to move forward to the concept of circular convolution. Okay, circular convolution is very good for these items. Linear convolution between a signal xi of duration n samples and a signal hi or a system hi, okay, is the same. Signal hi or the system hi in the formula, not in the real. Signal hi of duration, for example, L, L maybe not equal. L samples is a signal y, and with duration of n plus by L minus 1. That is n minus 1 plus L minus 1 plus by 1. Okay, that means L plus n plus by L minus 2 plus by 1. That is n plus by L minus 1. This is the formula. yi is sigma xk hi minus k. This is the formula. Okay, we said about convolution. In we have an input and we have impulse response of a system, and with this formula or convolution, linear convolution, we have the output. Okay, x over n items, h over l items, for example, y over n plus by L minus by 1 items. Okay, and we can write in vector format. Y is hx. Y hx. Y is hx. And this is y. Y is 0. Y n plus by L minus 2. From 0 to L minus 2. That is all of them plus n plus by L minus 1. Okay. Or is this y is h dot matrix of x. x is 0 to x n minus 1. مس عباس،
نحن محلول هذا إذا أمكن تأتينا بواجبات في التكالب.
Mr. Abbas, I knew some items, okay, but please you or other no, Mr. Abbas, you or other your friends, for example, Mrs. Dalal, other items, please type in English. Okay, I know what do you say, but please type in English. I know better. I knew so, okay. نحن نخافون لا تخافي ولا تحزني, okay, but I said don't worry. For example, takalif, okay, Mrs. Dalal. I said, for example, maybe we have more than 1 month, okay, maybe from the next week or other weeks. Each week we have exercise 1, exercise 2, exercise 3. After these theories, okay, we are in part 3, and we have totally 4 parts, okay, part 1, part 2, part 3. We are in part 3. After it, part 4, maybe in next week, okay. After it, exercise 1, exercise 2, exercise 3, exercise 4, maybe exercise 5. And exercise or projects are easy, okay. And you are, for example, you should deliver to me some video files, okay, some video files, for example, when you work in MATLAB, okay, in MATLAB package. And for example, I tell you, for example, some images with some histogram, for example, some functions, okay, some M file, and you are, for example, in working over your system and capturing a video file and delivering to me. Some easy projects, don't worry. Okay, Mr. Abbas and others, we are in theoric version this week, and inshallah the next week is the last one. After it, we start for project 1, project 2, project 3, experimental works. Ahsantum, Mr. Abbas. Ahsant. Okay, don't worry. Y is hx in okay, Mrs. Sarah. Okay, inshallah from next week or after it is starting. That's it. Linear convolution for one-dimensional signals in matrix form. Okay. If you expand the linear convolution, this form, y is hx. Okay. If we expand it, we see that the matrix X has this form. Y is hx, or y is this. For example, here, h0, 0, 0, 0, 0, 0, 0. h1, 0, 0, 0. h2, h1. h3, h2, h1. h4, h3, h2, h1. h5, okay, and hl-2, hl-3, hl-4, etc. To here, to and the last one, okay, 0, 0, 0 to hl-1. That's right. And you see in this diagonal, okay, h0, 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 all of this. h1, 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 and all for example, hl-1, hl-1, that's right. Okay, this is the form of H in linear convolution. Okay, this time for one dimensional. Observe that the elements of the descending of diagonals, these items, okay, are identical, h0, h0, h0. In linear algebra, this is a Toplitz's matrix, or diagonal constant matrix. These diagonals are constant, h0, 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 h0. Okay, is a matrix in which each descending diagonal, these items, okay, from left to right, has identical elements, and this time this h is the same, and this is good for us for simplifying, for example. What about circular convolution? That was linear convolution. Okay, linear convolution. Here, circular convolution for again one-dimensional signals. Okay, after it, circular convolution for two-dimensional, for example, signals. We form now the extended versions of FI and HI. Okay, we had FI and HI. We are constructing a new version of HI and FI named FE, or extended, or HAI, or extended version. Both of size m larger than n plus by L minus 1. Okay, for example, larger than this one. Okay, حداقل this one. Okay, larger. Both of size m that is larger than m plus by L minus 1 by 0 padding. For example, F has 10 items, okay, and H, for example, has 5 items. Okay, you can add to each of them, for example, add to F 5 items. I had, for example, F 10 items, H 5 items. You can add 5, 0, 0, 0, 0, 0, 0, a chain after H to both of them are 10. Okay, F is 10, H is 10. This is 0 padding. 5, 0 is added to, for example, the smaller one, to H. But this formula says F is smaller than n plus by L minus 1. In this example, F was 10, duration of F was 10, duration of H was 5, sum of them n plus by L, sum of them is 15, okay, and minus 1 is 14. That means m for both of them is larger than 14. Okay, that means you had add 4 at least 4 zeros to FAI, and 4 plus by 5 means at least or حداقل 9 zeros to HI after the samples of HI. Okay, after of them. This is the meaning of 0 padding. Okay, padding or adding some zeros after this chain of samples. 2m for both of them is larger than this item n plus by L minus 1. This can be denoted as FAE or FA extended I and HAE or HA extended I for circular convolution. Okay. Furthermore, we assume that both FAE and HAE are periodic with a period m. Why? Because both of them have this m. For example, 14. And we can assume. Okay. Okay, since both FAE and HAE are periodic in our assumption, their convolution is also periodic. Okay, with which period? Period of m. Okay, and this is named circular convolution. Is given by the expression YAE or YA extended is sigma all over the m. For example, k from 0 to m minus 1 all over the m. F extended, H extended, okay? F extended k, H extended I minus k, okay? And maybe plus by NAE, that's right, NA extended. This is these items, not plus by n. This item, the first one, this convolution is circular convolution, as this is noted as here. F extended I, circular convolved with H extended I, and maybe plus by NAE. This is outside of the convolution. Okay, here plus by NAEI. This is the meaning of circular convolution. Okay, both of them after zero padding have the same duration or the same period m larger than L plus by NA minus 1. Oh, hold on. Why? I connect the charger. Okay, I can share my screen. Okay, this is the page of 21. Okay. I share my screen, and after this two page, I go back to this file. Okay, for better speed of internet. I stop sharing. I share my screen, and here you see my screen. Okay. That's it. We had this slide. Circular convolution, Y extended is sigma over K, F extended, H extended, FK, HI minus K, okay? Or FAE, circular convolution with HA. This is circular convolution for 1D, one dimension. The slide. That's it. Using method notation, we can write the following form: H is y dot f, okay, for our f extended from 0 to m minus 1 y. This is wrong. Y or y is a matrix of f dot it matrix of h. Here is good, okay, and what is h? H is item. 2 h minus m plus by 1, h1, h0, h1, h2, h1, h0, h minus 1, h3, h minus 1, and this item h m minus 1, m minus 2, m minus 3 to h2, h1, h0. That's right. Here, starting from h0 ending to h0. Again, this descending diagonal is h0, h0, h0 identical. This is H1, 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 and etc. I decided to ignore any external noise. Okay, for example, for simplicity, for example, in effect of H system, not effect of noise, and we said Y is a synchronous convolution between H and F. Okay, note that in most real life scenarios, the size of HI is much smaller than the size of Fi. But because of Fi is okay. H is a system, not a signal, and it's a fixed system. For example, with some dimensions. Okay. But is at and incoming for seconds and seconds and seconds and okay, and Fi is very larger than in some larger than Hi. Okay, that is of Hi 0. Okay, in the periodic extension of Hi. Hi was small. Samples H extended of Y samples will be 0. Why? Because we said the size of both should be the same. M for Salaam alaikum, Mr. Ashrami Asadi Ahmed, or your name, first name is Ashrami or Ahmad? Ahmad, ahsant. This is typed as here. Okay. Based on the above comments, H will be a sparse matrix. In Persian, we say tonok, or I don't know what we say in Arabic, for example. For example, as a desert, okay, or for example, as a whole, okay, khali, you know what I say, Abbas, that's right, or Mr. Yasser Ali. Some of you, for example, this is Dalal, Mr. Yasser Ali. Okay, that's right. This H is called a sparse matrix. Continue. Refinement dimensional synchronous convolution. That's right. Because HAE is periodic with period M, we have H is again H0, H minus 1, H1, H0, H minus 1, this one, and that's it. Opposite structure is formed by the row above it if we push one position to the right. That means H0, H minus 1, H2, H1, H1, H2, H1, H0, H minus 1, H in this line. We have here H2, here we have H1, here we have H0, here we have etc. That's right. The element that is thrown out of the matrix in the row above because the mass left element in the row under consideration. For example, here it's 1 plus by 1. Okay, here you start with H1 and here H minus M plus shift from here to here for the row. That's right. This is a so-called circulant matrix. Okay, we are going about circular convolution. This is a circulant. Another one, eigenvalues. Eigenvalues of circulant matrix. Okay, but about eigenvalues. For example, we find what is by K? H0, He0. All of these items are E. Okay, here are fx and H. F0 minus 1 E powered by or exponential of J to K m ohm to K over m and to 1 exponential of J to m over m minus 1. This is for example exponential of J to m plus 1. Okay, this is for example He0 exponential of J to p m ohm dot 0 dot k. Okay, E power is 1. Okay, here this is 1 and where is it? Here, for example, k from 0 to m minus 1. Since E J m minus a, okay, m dot to be m to over m is because J to p over m dot m is J to p. Ej, okay, Ej to p dot k dot Ej to p m ohm minus a dot k. Okay, and this one was 1. Here is 1. Okay, 1 exponential of minus j. This is minus J to p m ohm I k. Okay, over m I k. Exponential of J to p m ohm or J to p over m minus m plus a. This is m minus a. This is minus m plus j. Is okay. Mirror of these items. M plus m minus I minus m plus I k is again m over m is j to k, and this is 1, and this is E to p over m I to p over m I k. That's right. This item, considering these two items in the slide, we have yk is to this item. Yk is H0 plus yk is H0 minus 1 E is to p over m k m minus 1 on k 1 j to m better version 0 0 m minus 1 1 1, and this is our m is unit and these items h0 h falan 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 is sigma or over the m. Okay, from sigma h e n exponential minus j to p m n k. This is a form. Okay, the used item. This is Fourier transform or discrete Fourier transform, DFT. The first form in the lecture. Okay, part 1 at this transform. This is form of DFT is get Fourier transform. That means this eigenvalue y(k) m this item, and all of this item is h(k). y(k) is m h(k). A is the DFT of h small I. H small I was impulse response, and this is, for example, we say in time, this is the frequency response of the system. Okay, or you can say this is in a spatial form, this is in frequency form, or the frequency domain. This is in a spatial, or we say makani, makan. In Arabic, you know makan, or position. Okay, spatial. This is in a spatial domain, and this is in a frequency domain, or DFT. That's right. Okay. So this is again eigenvalues and eigenvectors for a circular convolution or a circulant matrix. Okay. If we define WK as the example WK or weights, okay, exponential of 0. That means J2PM 0 is 1. For the 1 items, exponential of J2PM K dot 1. For the next one, exponential of J2PM K dot 2. And the first, then last one, all of them are M items. The last one is exponential of J2P over M called M1. Okay, the weight function, okay, or the weight matrix W. If it can be seen as that HWK is lambda WK. Okay, lambda WK. This is the meaning of eigenvalues. This item is eigenvalue, and eigenvector. YK is an eigenvalue of the matrix H, and WK, this is the eigenvector, and WK is corresponding eigenvector. This system is a good system H. Okay, that means this YK, or that means this input, this is the eigenvector. Okay, with these vectors is some items dot that vector. What is that item? This is the frequency response. Okay, or we had transferring from a spatial domain to frequency. A matrix U whose columns are the eigenvectors of matrix H. That's to say, for example, W is W0, M minus 1. Next slide. Continued. But for again, W cover A. Okay, not exponential. Exponential, we said it. Okay, exponential J 2p over m ki. Okay, k dot I said k 1, k dot 2, k dot m minus 1, for example, and W inverse. Okay, W inverse is 1 over m exponential. This is minus j DFT and inverse DFT. Okay, we can then diagonalize the matrix H as, for example, we say H is, what was H? You can say H is WD. Okay, no, we can write this eigenvectors so that we can write H, okay, the eigenvectors, vectors, so as we can write H is WD W minus 1 and WHW. But what is D? D is all of the items are 0 except this, the diagonal, okay? In this main descending diagonal is lambda 0, lambda 1 to lambda m minus 1. Obviously, D is a diagonal matrix, okay? And DKK 0, D1 1, etc. DKK is lambda k and is MHK. And the eigenvalue and this item W's was eigenvectors for H. That's right. All these are in circular convolution and DFT. If we go back to the degradation model, we can write the Y is HF, Y is WF, and for a solution W inverse Y, here is W inverse Y is this is I or order, okay, I identical matrix. D inverse F, W inverse Y, D W inverse F, right? We are finding the R system, the reverse system, that's right. All of these items. And Y frequency domain, okay, this is one dimensional. Y is MHF, okay, Y is MHF. F is the, and this is for the system HF, okay, and M is a scalar, no problem. Is a matrix product, okay. This FK is HK is the system response, okay. And what is H? H is the same as DFT, discrete Fourier transform. YK, HK, FK, all of them in M 0 to S1 are the M sample discrete Fourier transform of that means FI, HI, and YI, input, system, impulse response of system, and output, okay, respectively. That means the frequency domain convolution or circular convolution transfer to product, and product is very better and very simpler, okay, very simple. Circular convolution is so hard in the spatial domain, but in frequency domain, as for example Laplace transform, you say, for example, you have x at t and h at t impulse response of a system. What is y at t for a LTI system? Y is, for example, x at t convolved by h at t. But in Laplace form, you say Ys is xs dot hs, okay, and this is this item one dimensional, okay. In the spatial domain we have circular convolution, and in the frequency domain we have DFT. In circular convolution you should compute that sigma psilon, but in DFT you only should compute the product H dot F. That's right. So by choosing YK and WK as above and assuming HE is periodic, the last slides, we start with a matrix problem and end up with M scalar problems, okay. For example, this item is a scalar, this item is a scalar, and this item is a scalar, okay, and this is very good. and simpler for computing. The advantage of frequency domain to one advantage, not all of advantages. What good advantage of frequency domain over circular over the spatial domain instead of circular convolution, okay, or convolution. Okay, we go for this time for two-dimensional. To this time we was in one-dimensional, but because we are working with pictures, and pictures are for two dimensions, I and J, we extend that fundamental items, okay, circular convolution, excuse me, in two-dimensional signals, for example, for images. That's right. Suppose we have a two-dimensional discrete signal, for example, f I O J. For example, of size a dot b, okay, a dot for example, optional size a and dot b. Samples for I and j, which is due to a degradation process. For example, the output of the H system, okay. F is the input in these slides, but due to a degradation process means Y, not F. The degradation cannot be more a two-dimensional discrete impulse response of H. This H-I-J is the impulse response of the disturbance system, okay, or bag system that affects F. Of size, for example, C dot D, okay, this size for system. We form the extended versions of H dimensional I and J. Both are, for example, size of M dot L. M is, for example, A plus by C minus is larger than, not equal. M larger than A plus by C minus 2. M larger than B plus by D minus 2. This is here. M larger than A plus by C minus 2, and A, no, minus 1, I said minus 2. A, I said in the last slide, what was here? A minus 1 plus by C minus 1 plus by 1 because of 0. That means A plus by C minus 2 plus by 1 or minus 2. Okay, and A larger than M plus by B plus by D, okay, minus 1. And per the M dot N, these can be denoted at F extended IOJ and extended IJ dimension. Okay, this is essential for I to I and J. From this point forward, we will assume that additive noise NE is presented in the model, okay. That means here after this relation, Y is the relation plus by N. What is this relation? This is a formula for circular convolution, okay. Sigma over K and sigma over L. Sigma over K, all of the range from M items, okay, from 0 to M minus 1, and all of the items 0 minus 1, M dot N, FAE, HAE, FAE KOL, HAE, I minus K, J minus L, or HAE KOL, I minus K, J minus L. The result is the same. After it, plus by NAE, okay. Go next slide. Another one. After this item, a new one. Okay. Lexicographic ordering. In this section, we use a mean for representing all the pixels in image as a vector. Okay. All pixels as a vector. For example, picture as a point of IOJ. Okay. Representing a mean or a tools a tool. Example, as a vector. This can be done by staking the rows of the image on top of each other. Okay, staking rows of the image on top of each other. As for example, this is this is slide. Okay, this is slide. Okay, row 0, row 1, row 1, row 2, row 2, n. Okay. This is for axis of I, and this is for axis of J. I over m items and J over n items. F I O J I size m dot n. This is row 1, row 2, row n, and f. All of the f is of size m n, m dot n dot 1. Okay. Here, last slide. This can be done by staking the rows of the image on top of each other. Please, the next slide, I said, in this slide, okay? This introduces an alternative way for representing the degradation equation. In the, what was degradation equation? This is the degradation equation, okay? The effect of H system over F in this convolution plus by N effect, noise effect. This is the degradation model, okay, for a linear space invariant. That means LS system or LSI degradation process. We have this output based off this input, this formula. This is the degradation formula. This introduces an alternative way for representing the equation in the restoration problem. Okay, this item we are speaking about in this part. It becomes a vector matrix equation. That means the input output is y is f, okay, plus by n for noise. Y of f are m dimensional extension version. Okay. FAE and YAE, these items are FAE and HAE, are M dot N, not A dot B, C dot D. All of them, both of them, have MN dimension. MN dimensional column vectors in that represent the lexicographic ordering of images FAE actively. That's right. Okay, if the degradation is if the degradation system, for example, okay, if this system or if in this process, if the degradation process is LSI, linear special invariance, okay, LSI, then this matrix has a specific form, so-called block circulant matrix, okay, block circulant, because of this circular convolution. This form, like circulant. If the system was LSI, that means we can apply to it convolution. It's straightforward to describe this matrix in the spectral domain by finding its eigenvalues and eigenvectors. We said row 1 rows up stack over each other. Row 1, row 2, row 3 to row n. All of f input of size m by n. This is the I dimension, for example. Okay, x for example, and this is for example y or j axis. Okay, that's right. Excuse me. But about block circulant matrices. I mentioned in 2 dimensions the input output relation was y is hf plus by n, where the matrix h is a block circulant matrix and h is again as last h0 m minus 1, okay, m minus 2, m minus 3 to h1 circulant. This h transfers to this item. Here is h1. H1 H0, H minus 1, H minus 2 to H M minus 1, H0, M1, H1, H2. Again, the last one, H2, H0, H1, H0, H minus 2, and the last one, Hm minus 1, Hm minus 2, H2, H1, H0, and Hj, okay, Hj, for example, for one dimension, okay, and circulating by Hj is He, J0, J n minus 1, n minus 2 to H0, He is J0, and He J1. And this item circulates here for the next J01, J0, N minus 2, N minus 1, N0, 1, 2. Okay, the last one 2, 1, 0, minus 1, etc. The answer of the diagonalization of H is a straightforward extension of the one-dimensional case. In that case, we end up with the following set of m by n scalar problems. Y is mn. These are two scalars, two digits. Okay, m dot n. These vectors H, F. Okay, and maybe plus by n. H for 2 dimension, dot F for 2 dimension, and maybe plus by noise for 2 dimension. Okay, and we are in this relation in the frequency domain, U and V, not I and J. In I and J, or a spatial domain, we had convolution, circular convolution, and in U and V domain or frequency domain, we have FTs of the system. Okay, this large F a U of V is the FT of F a I o J, and this H a U of V is the FT of discrete Fourier transform of H a I o J. Okay, and maybe plus by noise in frequency domain. All of them, U is M and V in N, M dot N. That's right. These are block circulant matrices, this H. Okay. Excuse me. Periodic extension of images and degradation model. In image restoration, we often work with discrete Fourier transform, as we saw. Okay, in the next lesson, we often work with discrete Fourier transform, or DFT. DFT assumes periodicity, okay, of the signal in time or space. But this time in a space, okay, in we say H small I or H I o J, and we say H large H in frequency domain. Okay, but H is periodic in time domain, H small is H. No, I can't type here. Okay, because my screen share. No problem. This item. No. And okay, this is good. And this is good. Yeah. Right. That's it. This is H in time domain or in a spatial domain. A spatial domain, not time domain here. A spatial, and this is in frequency domain. Okay. Both of them, this H and this periodic. Okay. Here DFT assumes periodicity of the signal in both of time and space. This H is periodic. This is in spatial, this is in frequency domains. Therefore, a periodic extension of signals is required. We said both of them after F and H, F input signal and H the system should be extended, okay? HE and FE, and we say periodic extension of signals is required, okay? This extension required. Distorted image, that means Y, YIJ. Distorted image is the convolution of the original image, F, and the distorted H. Y is a convolution of F by this because of the linearity and space invariance assumptions. We said if a system was LSI, if was that you say Y H convolved by F or F convolved by H. The results are the same. Convolution increases the size of signals. We said, for example, N into M. M is N plus by L, for example, minus. L increases to M again, okay? What is M? M is N plus by L minus 2. That means the size of output is larger than the size of signal and the size of system, okay? Size of H and F. Periodic extension must take into consideration the presence of convolution. That means zero padding is required, because we want to use this relation of convolution. We need to zero pad to both of them, not to the smaller only. To a smaller only to reach the bigger one, and to both of them required by, for example, N by L minus 1. Every signal involved in an image restoration system must be extended by zero padding. Every signal must be extended by zero padding and also treated as virtually periodic. Virtually periodic, okay? Not maybe real periodic. That's almost all of these lines was repetitive, okay, or tekrar from the last, and you knew that items. Again, wrong periodic extension of signals, okay, and in the next slide, correct periodic extension of signals. Both of them, red and green signals, are convolved, okay, and here this is the wrong, this is red, this is blue, for example, or red and green. This red, this green, two signals, okay, are convolving. But here, this is correct periodic extension of signals, okay. But no, but here, if you choose, for example, M or N lower than that at least, or that حداقل, we said, for example, M should be larger than or small by, for example, N plus by L minus 1. If M of, or if the items, okay, is smaller than that items, you wanna, okay, and you see that the green and the rims are intermediate each other, okay, or disturbed, okay, or disturbance. That's right. A wrong periodic extension of signals, red and green signals are convolved, but in the bad way, okay. Why? Because we small zero padded. This zero padding is small, okay, or this zero padding is small. but in this correct version, correct predict run, this zero padding is large, okay, or between these two items this zero padding is large, okay. The difference between this item and this item and this, okay, you can insert this item here, okay, without any disturbance. As for aliasing, okay, as for aliasing phenomenon is a good one, and the last one was a bad extension, not zero padding or a small zero padding. This is bad, but this item is very good. That's right. Here you can see as this item, this green is inserted here because of this duration, this large duration, or this item is inserted here because of this large distance, okay, or guard, okay. This red here is this black as here, okay, no worry. For example, here you see you have another, for example, item as here, okay. This is the same as this, for example. This is circular, and again this item no, after it you see this rectangle, after it you see this, for example, triangle, and etc. This verdict. This is a good version with a good distance or a large M, okay, and this was a bad version or a small M, smaller than that threshold. M should be greater or equal by n plus by L minus 1. That's right. This item, correct verdict extension of images and degradation model. If we had correct, okay, or a good item, M is smaller than, larger than falan, okay, the original image F is of size A dot B. The degradation model or H is size of C dot D, okay. We form the extended version of F and H, or FAE and HAE, by zero padding, both of them by size of M dot N, and we said M is larger than A plus by C, okay, and minus 1, and N again larger than B plus by D. A plus by C, no, this item, for example, for the first one, A plus by I don't know why, I can't type. A plus by and B plus by D, okay, larger than these two items, or minus 1. M, or if you remove this equal, means M larger than A plus by C, and N B plus by D. Okay, example, for example, some images, for example, image 256 by 256, A and B are the same, for example. Degradation, this is C and D. Again, C and D are the same, C and C, A and A, 256, and C and C, 3 by 3, okay. With extension by zero padding, both images, not both images, or maybe, for example, two images. For example, it said image green and image red, okay, or a system and a system and an image, okay, or two images to one system. Extension by zero padding, both images, we have dimension at least this item, A plus by C minus 1, and again B plus by D minus 1, or 258.250, for example 6, okay, at least, or maybe larger. They are also assumed to be again periodic with this period for M and with this period for N. Go to two other slides. Again, here you see periodic extension. Continue to see extension. This is the meaning of periodic. This picture over I, okay, and over, for example, J. This picture, okay, and periodic to this in this axis, and periodic in this axis. This axis and this axis and this axis and this axis. This is the meaning of periodic extension. Periodic, not zero padding. Periodic extension. And this is the a sort of another concept, inverse filtering. Okay, for this part for registration. If you have some problems or some questions, I answer you. In answer to Mr. Yasser, inshallah, I said, inshallah, this night, I add that lectures to LMS, okay? Another question, if you have, I'm answering. Or not, I say, Allah ma'akum. قربانت Mr. Yasser Ali. Fedak. Qurbanat means fedak. قربان شما. I stop sharing. Oh, okay, Mr. Yasser. Yasser Al-Tamimi. Okay, Mr. Yasser Al-Tamimi. That's right. Okay, if there isn't any question, I say Wassalam, or in Persian, Khuda Hafiz. Oh, Khuda Hafiz. Khuda Hafiz Hamigi.
What do you say? Anam موجوده? Mrs. Sabah, what is Anam? Mrs. Sabah,
what is Anam? Oh, أنا موجود. Okay, أنا موجودة. That's right, Mrs. Sabah. Okay, don't worry. I name you your names. Mr. Abbas Al-Azawi, Mr. Ahmad Qasim, Mr. Ali Zubaydi, Mrs. Dalal, Mrs. Dena, Mr. Hamid, Mrs. Lom'e, Mrs. Sabah, Mrs. Sarah, Mr. Yasser Ahmad, Mr. Yasser Tamimi, Mrs. Zainab, Mr. Ahmad, okay, and Mrs. Maryam. That's right. Ahsantum. Okay. حاضرم قربانت. Okay. And last item, مع السلامة. الله معكم.